The scientific method is the single most powerful tool humanity has ever invented for understanding reality, because without it, none of those other tools would mean anything. And tonight, we're going to show you exactly how it works and exactly what it looks like when it doesn't, using one of the most common flat Earth arguments as our test case.
Here's the thing. You don't need a PhD to do good science. You don't need expensive equipment or a laboratory. What you need is a process, a specific sequence of steps that protects you from the one thing that undermines all of us equally, experts and beginners alike, our own bias.
We received some comments on our last video from flat earthers, claiming the sun is only 6,000 miles above a flat Earth, orbiting above us like a clock hand. It turns out this is a pretty key claim of the flat Earth models. And we thought, you know what? Let's not just tell you why that's wrong. Let's use it to show you how to think about a claim like that. Any claim, actually. Because that skill is worth a lot more than any single debunk of an ad hoc, out-of-left field theory of the cosmos. By the end of this video, you'll have something genuinely useful. A way of looking at evidence that you can apply to anything. By the end of this video, you'll be able to apply the scientific method. So what exactly is the scientific method? At its core, it is a sequence of steps, and the order is the most important part. Let's walk through it.
Step 1 is observation. Something happens in the world that catches your attention. Maybe you notice the sun appears to move across the sky. Maybe you notice that objects fall when you drop them. You don't need a hypothesis yet. You don't need an explanation. You just need to notice something and write it down. That's it. Observation is cheap, and it's where everything starts. Step 2 is the hypothesis. This is where you propose an explanation for what you observed. Here's where the first really important rule comes in. Your hypothesis has to be falsifiable. What does that mean? It means your hypothesis has to make a prediction that could, in principle, be wrong. If I say an invisible force pulls objects downwards, that's a start. But if I say an invisible force pulls objects downward, and therefore if I drop this ball, it will fall at exactly this rate, now we're talking. Now I've stuck my neck out. Now I've made a commitment that reality can either honor or punish. If your hypothesis can absorb any possible result, if no observation could ever contradict it, then it isn't actually saying anything about reality at all. It's just a story.
This is one of the most important ideas in the history of science. A hypothesis is not just made credible by being confirmed, it is made credible by surviving attempts to destroy it. The willingness to be wrong is what makes you trustworthy as a scientist, professional or otherwise, and it's what makes it science instead of mythology.
Step 3 is the prediction. This is where you take your hypothesis and ask, okay, if this is true, what should I expect to see? This has to happen before you collect your data. And I want to really emphasize that order because this is where most bad science and essentially all pseudoscience falls apart. Think of it like a bet. If I tell you I predicted the winner of a horse race after the race is over, that prediction is worth exactly nothing. It costs me nothing to be right. So being right tells you nothing about whether I actually understood anything. But if I tell you before the race, write it down, seal it in an envelope, now my prediction has skin in the game. Now if I'm right, that actually means something. Science works exactly the same way. Your prediction has to come before your data. That's what makes being right actually count.
Step 4 is the experiment. Collecting the data honestly, with a consistent method, and recording what you did and what you actually found rather than what you hoped to find. That's one thing we call confirmation bias actually in science. And step 5 is analysis. Do your data match your prediction? If yes, your hypothesis survives this round of experimentation. It doesn't mean it's proven. It means it passed one test and gets to face yet more. If not, your hypothesis is wrong and you must go back to step 2 with new information.
And here's the part that matters most for what we're going to do tonight. What happens when the data doesn't match the prediction. In real science, you go back and revise the hypothesis. That's fine. That's the process working exactly as intended. But, and this is critical, when you revise it, you have to go back to step 3. You have to make a new prediction before collecting new data and test it again. You don't get to look at the data that just proved you wrong and immediately construct an explanation that fits it. It's tempting, but it is bad. And it is one of the most natural, most human, and most scientifically poisonous things you can do. It even has a name. It's called post hoc rationalization. And the reason it's so dangerous is that it feels identical to real reasoning from the inside. Your brain will generate a confident, coherent, satisfying explanation for why the result actually supports your idea if you let it. The prior prediction rule exists specifically to stop that from happening.
This is the difference between a model that's getting stronger and a model that's just getting patched. When a hypothesis survives a genuine test, in other words, one it committed to before the data came in, the space of possible worlds gets smaller. We've ruled something out. And knowledge is, in a deep, deep sense, exactly that. The progressive elimination of ways the universe could have been, but isn't. Each test that passes is a real brick in the structure of humanity's body of knowledge. Our collective understanding of reality grows more solid, more trustworthy, more true. Post hoc patches do the opposite. They look like building, but they're just patching over the cracks. The structure isn't actually getting stronger, you're just hiding the damage. And because no test is genuinely ever risked, no knowledge is ever genuinely gained. You end up with something that looks like an explanation, but contains exactly zero information about how the world actually works.
So let's actually do this. Let's take the flat Earth model seriously on its own terms and run it through the process we just described. The flat Earth claim is this. The sun is a small local object about 6,000 miles above a flat disk, and it circles above us like a clock hand to create day and night. That's their model. Fine. Step 1 is done. We have an observation to explain, which is the day-night cycle and the sun moving throughout the sky. Now, let's move on to step 2, the hypothesis. The flat Earth hypothesis is that the sun is nearby, and nearby has a consequence that we can calculate. If the sun is only 6,000 miles up and moving in a circle above us, then its distance from us changes dramatically over the course of a day. At noon, it's almost directly overhead, closest approach. By late afternoon, it's off to the side, much further away. Distance matters because how big something looks depends on how far away it is. The further away something is, the smaller it appears. Every camera, every eye, every telescope in history agrees on this. It's just how light works. Let's take our hypotheses now and make a quantitative, falsifiable prediction from it using mathematics. The predictive power of these models is derived from the size of the sun in the sky, which is an immediate and obvious differentiator. The ratio of size to distance of a telescope to a celestial object results in something called an angular size, which gets smaller as the object gets further away. In the case of a round Earth model, the Earth is rotating, not changing distance from the sun. So the sun stays basically fixed up to the Earth radius, which is an effect of less than 1 part in 10,000, effectively negligible. But by contrast, the flat Earth model claims that the sun is passing overhead at a constant orbital height, which is what causes the day and night cycle. When the sun is at its closest, it's noon, and when it's at its farthest, it's midnight. Since the orbital height is given by the flat Earth model, we can predict by how much the sun's size should change. The distance from the plane of the Earth to the sun in this model is h, as shown here. At any point, the sun forms a right triangle with the telescope viewing angle, with one leg h and the hypotenuse of the triangle being the distance to the sun. Using trigonometry, we can relate the sides of the triangle to the telescope angle. This lets us find that h is equal to the hypotenuse times the sine of the telescope angle, and therefore the distance to the sun is h divided by the sine of the telescope angle. Now, how do we go from this to the size of the sun? Well, we know that as the sun gets closer, it should appear larger, and as it gets farther, it will appear smaller. If we call the size of the sun d, it forms another right triangle with the telescope, with one leg being d divided by 2. The angular size is the opening angle of this triangle, A. If we call the hypotenuse here x, we can use the tangent relation, tangent of A equals x sine A divided by x cosine A. Remembering the relationships from earlier, if we substitute the sides of the triangle in for the numerator and denominator, we get this nice expression for the angular size. There is an overall size set by the size to distance ratio, which is then modulated as the angle of the telescope changes, implying the sun is getting further away. The prediction for the globe model is quite similar, except there is no change with angle on the sky. So this triangle stays at the same distance always, and the height is simply the ratio of the size to the distance. If we plot both of these predictions, we can see they are very different, and it should be easy to tell them apart with some real data. So there we have it. Two models, two predictions sitting right next to each other, and they couldn't be more different. The flat Earth model predicts the sun's angular size should rise and fall dramatically across the day, biggest at noon when the sun is closest, shrinking toward the horizon as it moves away. The round Earth model predicts it should essentially stay constant because the sun is so far away that its distance barely changes at all from our perspective. This is step 3, our prediction. We are making this prediction right now before we take a single frame of data. We're writing it down, we're committing to it. The flat Earth model says the sun should shrink dramatically towards the horizon. The round Earth model says it shouldn't. That's the bet on the table. Now, we go collect the data. And whatever the data says, we have to accept it and move from there.
This is exactly what the scientific method looks like in practice. A claim has been made. We derived what that claim predicts, we stated that prediction out loud, and we made our bet. And now we test it. Notice what we haven't done. We haven't looked at the data first and then decided what we were predicting. We haven't left ourselves any wiggle room. If the sun shrinks towards the horizon, the flat Earth model gets a point. If it doesn't, the flat Earth model has a serious problem. Those are the only two options, and we've agreed to them in advance. This is how we do science and how we unambiguously make sure the things we are learning are reflective of reality based on facts and describable, predictable observations, and not just bedtime stories we're making up on the spot.
So, how are we actually going to measure this? We need to consistently photograph the sun at different points throughout the day and measure its angular size in each image. The key word there is consistent. The whole measurement lives or dies on whether we're comparing apples to apples. If your zoom level or focal length changes between shots, your measurement is meaningless. So, we need a setup that stays locked. We're going to use the C-Star S50, which is a small, affordable smart telescope that's become popular with amateur astronomers over the last few years. And it's actually ideal for this particular experiment. Unlike a phone camera or a DSLR with a zoom lens, the S50 has no continuous zoom functionality. The focal length is fixed. Every single image it produces is taken at the same optical configuration, which means any change in the sun's apparent size from image to image is real, not an artifact of our equipment. Now, we know what some of you are already thinking. The S50 is a computerized telescope, it uses software processing as part of its image production, and someone is going to say that means the images aren't trustworthy. So let's address that directly. The software processing the S50 applies, stacking, noise reduction, sharpening, does not alter the angular size of objects in the frame. It's the same class of processing that every modern astrophotography workflow uses, including the ones used by professional observatories. The sun's disk occupying a certain number of pixels in the image is a function of the optics, not the software. And if you don't want to take our word for it, you don't have to. Take your S50 outside right now and point it at something far away. A building, a tree line, a distant hillside. Does it look normal? Is it faking anything? Is your neighbor's chimney doing something physically impossible? You can answer that question yourself in about 5 minutes without us, without NASA, without anyone. Which brings us back to the point, you don't need to trust any of this. Any telescope with a proper solar filter and a fixed focal length will do exactly the same job. Point it at the sun, photograph it at regular intervals from sunrise to solar noon to sunset, measure the disk size in each frame. The equipment list is a telescope, a solar filter, and something to capture images at a consistent setting. That's it. You can reproduce everything we're about to show you from your own backyard with your own hands and reach your own conclusion.
So we've now got our images. How do we actually get a number out of them? It's pretty straightforward actually. For each image, we identify the edge of the solar disk and measure its diameter in pixels. That's it. We're not converting to any physical units, we're not making any assumptions about distance or size, just pixels. Raw, direct, assumption-free pixels. And because our focal length is fixed throughout the experiment, pixels are a completely honest representation of angular size. If the sun looks bigger, it is bigger. If it looks the same, it is the same. We then normalize everything to the noon measurement. So noon gets a value of 1, and every other measurement is expressed as a fraction of that number. This method lets us compare directly to both models, regardless of the actual size of the sun in our images. It also gives the flat Earth model as much leeway as possible. That way, if their distance measurement is incorrect, but the general idea is sound, they will not be penalized for it. Each image gives us one data point, one measurement at one moment in time, each with its own uncertainty based on how cleanly we can define the edge of the disk. So what we end up with is a series of measurements across the day, each with an error bar plotted against the two predictions we committed to before we started the experiment.
It's time to look at the results. The flat Earth model predicted the sun should shrink dramatically toward the horizon, following that sine curve we derived earlier, dropping to roughly half its noon size by the time it gets low in the sky. We gave it the best possible error bars. We locked our equipment so nothing could drift. We did everything right. And the data is a flat line. Flat in a way that is completely inconsistent with the flat Earth prediction, even after we bent over backwards to be as generous as possible. The round Earth prediction that the sun's angular size should stay essentially constant all day because it is 93 million miles away describes our data perfectly. The flat Earth model, even with inflated error bars and every statistical courtesy we could possibly extend, fails. That's the result. Now, let's talk about what it means.
Remember what we said at the beginning about what science actually does? Every honest test that a hypothesis survives eliminates one more way that the universe could have been but isn't. Our collective understanding becomes more solid, more trustworthy, more true. Today we ran a real test. We stated a prediction before we collected data. We used consistent equipment. We applied fair statistics, and we arrived at a clear answer. That answer adds a brick. It doesn't add a brick because we say so, because we have PhDs in astrophysics, or because NASA agrees with us, but because the process followed the scientific method. The prediction was committed to in advance. The test was real. The result was unambiguous. That's how knowledge actually accumulates. That is how the human race advances. That is how we learn things that we can trust.
Now, I want to talk about the flat Earth response to this because we know what it's going to be. It's going to be perspective, and it's going to be atmospheric refraction. It's going to be something. And I want to explain why that response, whatever form it takes, is not science. We derived a prediction from the flat Earth model. We tested it. It failed completely. If you want to save the flat Earth model now, you need to propose a specific quantified physical mechanism that explains why the sun's apparent size doesn't change the way your own geometry demands it should. Don't just throw words around. You need a number, a formula, something that makes a new prediction we can go and test. Atmospheric refraction is a real thing. It's well understood, it's fully quantified, and it affects the position of the sun near the horizon by about half a degree. It does not affect angular size in any meaningful way, and it absolutely does not account for the factor of 2 size change the flat Earth model predicts. That's not our opinion, that's just a calculation anyone can do. Perspective is not a mechanism, it's a word. And as we discussed earlier, perspective is the angular size relationship. Invoking perspective to explain why angular size doesn't change the way geometry says it should is like invoking gravity to explain why something didn't fall. So therein is the challenge to the flat Earth model itself. When you are doing science, you have to produce a quantified, testable, falsifiable mechanism that explains the result. Derive a new prediction from it, and then go test that prediction before you look at the data.
And this is fundamentally why the flat Earth model cannot survive contact with the scientific method. The scientific method requires you to risk being wrong. It requires you to make a call before you even see the cards. Flat Earth discourse does the opposite. Every failed prediction becomes a new patch. Every patch is constructed after the data are already known. No new prediction is ever committed to. Seeing all the shrine to Beau Morris here, my lovely 11-year-old son who is fascinated with astronomy and is committed to the scientific method. No test is ever genuinely risked. And because no test is ever genuinely risked, no knowledge is ever genuinely gained. And no amount of patching can change that. This is what it looks like when a model has stopped engaging reality. Even my 11-year-old son knows that.
Look, if you came into this video believing the Earth is flat, I'm not expecting you to walk away convinced. That's not really how it works, and I know that. But I hope you walked away with something more useful than just a debunk. You now know what a real prediction looks like. You know why it has to come before the data. You know what falsifiability means and why it matters. You know the difference between a patch and a revision. And you know that you can go outside, point a telescope at the sun with a solar filter, and check every single thing we showed you tonight with your own eyes and your own hands. Go check it yourself, and then tell us what you see.
The scientific method is not some elitist weapon scientists use against people who disagree with them. It's a gift. The best tool humanity has ever built for finding things out while protecting yourself from your own blind spots. It works the same way for everyone, everywhere, regardless of what they believe going into the experiment. All it asks is that you ante up and place your bet before you see the cards. That is the nature of science.